Have we not done this? Has no one done this yet? Okay, then I'll just give you a minute to try the calculation, see how far you get, and ask questions when you hit questions, and then we'll go through it together. I'll give you a minute and go. Paisley has a great question. What do we use for C for food? Do we have a C for food? A specific heat capacity for food. Do we have that? You can nod or shake your head. You can give me a thumbs up, a thumbs down. You can type into the chat. No, we don't have that. So we are missing the C. We're missing this for food. We don't have that. And food is kind of weird. It doesn't really have a heat capacity. It gives off heat. It doesn't really absorb heat and change temperature, right? So you can't actually calculate the Q of food. We have to get it a different way. Any suggestions? Yeah, you have to calculate Q of water first, and then assume that whatever the water absorbs is the food has given off. Okay, so go ahead and do that. Yeah, so you don't have enough information to calculate the Q of the food. You have to calculate Q of the water first, and then assume that whatever the water absorbs, the food has given off. So we're calculating Q of water, and I'm giving you a head start. Yes. Okay, so let's check ourselves here. Is it reasonable for this to come out positive? Or did I do the math backwards and it should have come out negative? Yeah, it's absorbing water. The water's your system, so energy is going into your system. It should be positive. Okay, so if the water absorbed this much energy, then the food must have given off that much energy. Okay, so what should be our sign for the food, positive or negative? Q of food should be positive or negative. Yeah, if the food is your system, energy is leaving the system, so that one should be negative. Okay, now a good question here would be, considering our system, or considering our setup, I should say, considering the setup that we had and it's all of its glorious imperfections, should the Q of food be higher than it actually is, or should it be lower than it actually is? Considering the error that our system had, the actual Q of the food, should it be higher than this or lower than this? And I mean magnitude, like a bigger magnitude or a smaller magnitude. Sorry, with negatives it gets confusing. Yeah, so we definitely lost some energy from the food to the water. So the Q of the food, since we're basing it off the water, which has lost energy in the process, the Q of the food is going to have a greater magnitude, a bigger magnitude. Or you could also say the Q of the food should be more negative. So this is a great example, or maybe a non-example, of when you're answering those questions, you want to be really careful about what you say. So you could say greater magnitude, or you could say a more negative QF. Because higher and lower, I guess, is pretty shady, pretty subjective. Okay, that's it. That's Q of food. This is why I love it. So separated. There's not a whole lot you can do with that. Did I ask you any post-lab questions on that one? Oh, okay. So in this one, the last question in the post lab is asking you to calculate the enthalpy of the food. So the enthalpy of the food, you may not know how that's different than the Q of the food, and so your key is in the units that are listed. So looking at the units that are listed, tell me what the difference between delta H of the food and Q of the food is. Yeah, let me say it again. Okay, so if you are looking at the enthalpy document, let's see, what day did I post that? Wednesday? Yeah. Okay, so if you're looking at this lab document, okay, and we go down to the part that's talking about the food. Okay, right here. So see the post lab here in gray. It's asking you to calculate Q of the water, which we did. It's asking you to calculate Q of the food, which you did. And now it's asking you to calculate delta H of the food. So you may not know what the difference is between delta H of the food and Q of the food. And so what you should do to investigate that a little bit is look at the units. What are the units of Q food and what are the units of delta H food? How is delta H different than Q? Let me see if I can turn my video off, if that helps a little bit. Give me a second. Okay. Let's see if that makes it any better. I just turned on the video on my second machine. Okay, but I typed it into the chat. How is delta H different than Q of food? Look at the units listed. Any ideas? Okay, so that could be a difference. Q is in joules and delta H is in calories. Sometimes that is the case. You can report enthalpy in calories or joules. That is a difference listed here. That's not always the case. Look at part 5, heat of neutralization down here. Notice that delta H there is in terms of kilojoules, right? So you can list it in terms of calories or joules. What's another difference? Okay, is this one? Oh, wait for it. Huh? Is this one better? Am I cutting out on this one or no? This one's better? Okay. Yes, it's per amount. Yeah, it's per gram or it's per mole. Yes. Yeah, so how do we go from, let's just ignore the fact that this is in calories. I think that's dumb. We're going to change this. Okay. Is that how you spell joule? I think so. Okay, so if it's in terms of joules per gram, how do we go from Q to H? How do we go from heat of the food to enthalpy of the food? How do we calculate that? Good guess. What's the molar mass of an almond? Doesn't have one. I mean, I'm sure you can find it somewhere, but it's not an element or a compound, right? An almond's a mixture. So that's a good thought. But since we're not dealing with an element, we can't go that route. What's another route? Ooh, Cyrus and Sydney. Yes, divide it by the amount of grams we had. Exactly. So you're going to go from our amount here in joules, and then you're going to take that and divide it by the mass of the almond. So negative 1.09 times 10 to the 4th joules divided by the mass of the almond, which was, exactly 1.0 gram, which is a coincidence, and it usually doesn't work out that nicely. Come on, almond. Teach us some lessons here. Okay, so delta H in this case is 1.09 times 10 to the 4th joules per gram. But if the mass wasn't 1.0 grams, then that amount would have changed. And it definitely will on part 5. Okay, questions on this section before we move on to the salt, to the lithium chloride one? Or comments or emotions? I'll take all 3. Questions, comments, and emotions. All right, let's deal with the salt. So this one had kind of a lot. So if you look at that table, it has like mass of the salt, mass total, which would be salt and solution together. It has temperature change. So all of that is just like data, right? And then it has Q of the solution and Q of the reaction. So this is what your warm-up was getting at. It's a little bit different than the like hot water, cold water, because it's so mixed together. I mean, how do you really distinguish between the reaction and the solution? That's tricky to do, right? So which one do you think we can calculate first? Nice. Yeah. And this is a good way to decide if you are kind of stuck as to how to start your calorimetry problem. It's nice to decide, like, okay, what could my system possibly be? And what would that equation look like? You know, if it's Q of the solution, everything has to be of the solution. If it's Q of the reaction, everything has to be of the reaction. And we do have a mass of the reaction, right? We could do the mass of the base and the acid, but we don't really have a C of the reaction. What would it be as the specific heat of? Like the specific heat of the salt? But we didn't really start with the salt. The specific heat of, I don't know, them together. We don't really have this. And then same with temperature. We don't really have a temperature change for the reaction, right? We didn't track the temperature change of the hydrochloric acid or the sodium hydroxide by themselves. We tracked the temperature change of the solution. So really the only one you can calculate is Q of the solution. So let's go ahead and do that for the three. Sorry. I'm talking about the neutralization one, but this is the salt one with lithium chloride. Okay, but it's the same thing. We really don't have a C of lithium chloride. We also don't have a temperature change of lithium chloride. So we need to calculate Q of the solution. So let's go ahead and do that. Mass of the solution, C of the solution, which is going to be 4.18 joules per gram degrees Celsius, because we're assuming it's the same as water, times the temperature change of the solution. All right, here's what I got. How about you guys? Paisley, you do need a Q of the reaction, right? Because the table asks you for it, but you're not going to calculate Q of the reaction. How are you going to find Q of the reaction? Yeah, it's the opposite of Q a solution. Whatever the solution absorbed, the reaction gave off, right? So if Q of the solution absorbed 2,580 joules of energy, then Q of the reaction gave it off. Q of the reaction is going to be negative 2.58 times 10 to the third joules. Okay, and this is kind of a moment for me. Just give me my moment here for a second. This is really the first time that we have directly observed a bond giving off energy. It's kind of cool, right? Like, we've talked about that for a really long time, maybe even years if you count chemistry or middle school or elementary, where you talk about like digestion and stuff like that. But we're holding physical evidence of a chemical reaction. So your salt separating, the lithium chloride bond separating, actually separating and giving off energy. I kind of think that's cool. I'm kind of a nerd, but that's okay. Okay. So here we have Q a solution, here we have Q a reaction, right? Now the next thing they're going to ask you for maybe, if my mouse will work, is delta H in kilojoules per mole. So enthalpy in kilojoules per mole. So how do we find that? And it's got to be enthalpy of what? The unit should give you a hint. We're going to have to divide by what? Moles. We're going to have to divide by moles. Now here's the catch. Moles of what? Because we have moles of acid, we have moles of base, we have moles of solution. Good and brave guess, Kaya. It's not going to be enthalpy of solution, although you could calculate that. In fairness to Kaya, that could be an option. Happy December, Kaya. Okay, I'll give you a hint. It's not moles of solution, it's not moles of acid, and it's not moles of base. What is it? Who loves riddles? And who just wants me to tell them? At least Claire's honest. I'm going to put that in your letter of recommendation, Claire. It's going to be moles of your reaction. So here's what you have to figure out, because if we do moles of acid, but acid is our excess reactant, then not all our acid has been pulled. Oh, sorry, it's not acid. It's lithium chloride. Oh my gosh. You people need to stop me when I start talking about acids and bases. Just someone, is there like a slapping emoji? Good heavens. I really want to get to part 5 and talk about neutralization. Okay, so obviously it's not going to be the acid or the base because that's not the part we're on. We're on lithium chloride. Oh my God. Okay, so it's going to be moles of lithium chloride. We're all going crazy, and not we all are going crazy. I'm going crazy. I'm going crazy, and you guys are along for the ride. How do you feel about that? Okay. So to get to delta H, you're going to take Q of your reaction, which is lithium chloride and nothing else, and you're going to divide it by moles of lithium chloride. We just need to leave this problem. I spent the morning arguing with my chemistry students about talking to one another. None of them would talk to anyone else. And I think I just lost all my brain cells in arguing about that. Okay, you're going to divide by moles of lithium chloride, and that is your answer. Now, I do want you to repeat this for the 3, 6, 9, and 12 because you're going to notice a pattern. In next class, that's the first question I'm going to ask you. What was the pattern that you saw when you calculated this delta H, this change in enthalpy for 3, 6, 9, and 12? Okay, let's move on, shall we? Is everybody good with moving on? Okay, let's move on. I finally get to talk about neutralization. Okay. We are on part 5, neutralization, and we are going to calculate Q of the solution first. So, because it's the exact same scenario as the last one, we don't have the information we need to calculate Q of the reaction for this neutralization reaction. We could calculate a mass of the reaction, but we don't have a C of the reaction. And we don't have a delta T of the reaction. We have these things for the solution, but not the reaction. So we have to calculate Q of the solution first. Let's do that. Good thing everyone's here today, because this would not be a helpful video to watch. All right, I ran into an issue. Did anyone else run into this issue? I don't have an initial temperature because my 2 initial temperatures are different. What should we do? Yeah, we're going to average them. The 200 was the mass of my entire solution. So my entire solution is the solution of hydrochloric acid, which was 100 milliliters, and the solution of sodium hydroxide, which was another 100 milliliters. So I have 200 milliliters total, right? And if you multiply that by the density of water, which we're going to assume that it's close enough to water that we can do that, 1 gram per 1 milliliter, right? Then we can just transition it over to grams. Yeah, you got to average them. So if your initial things are different temperatures, just average them. I look back on old tests to see if they ever make you do this. And I found like one multiple choice question that they made you do this. Everything else, they always give you the same initial temperature for your two solutions that you're mixing. So that's a good thing. It's a good thing to know. Okay, so I got 1.52 times 10 to the 4 joules. So that's Q of solution. What's Q of reaction? Yeah, so Cyrus, good question. If the masses of the two solutions were unequal, it would probably be better to do a weighted average than just a straight average like we just did. Yeah, that would probably be more accurate. Okay, Q of reaction. Yep. You guys are noticing the pattern. It's a good thing to notice. And then, do they ask you anything else? Oh, delta H in kilojoules per mole. So this is the tangent I was going off on the last problem. Okay, when you divide by the moles, it's not going to be moles of acid, because if you don't react all your acid, you're not going to release all the energy contained in that acid. Same thing for base. So what you have to divide by is the moles of the reaction. How many times does this reaction happen? That's what you're going to divide by. Now, it is a 1-to-1, right? So what you have to figure out is which one is your limiting reactant, and then the moles of your limiting reactant is the moles of your reaction, the number of times your reaction can happen. Now, I think I did it pretty carefully, and I think the moles of acid is equal to the moles of the base. So I think you can use either one. Ooh, we're so good. Class ends in a minute, and we just got through all of our calculations. Okay, so if anyone has questions, I can answer those. What I would say is go try some book problems. The hardest part of these questions is figuring out where to start. What do you have and what can you actually calculate? And that takes practice. Like me showing you is not going to help you learn that. You trying it and bringing your questions in will help you. So try some of them from the book. And if you have questions, we can talk about them in class tomorrow too. Good job today. Way to ride the wave of my crazy. I appreciate you guys.
I have one last question.
I'm ready.
So you were talking about, maybe I missed it, but enthalpy and having to use the moles of the reaction. So is that, why for enthalpy do we use the moles of the reaction?
Well, so if you use for enthalpy, if you use the moles of the reaction, you will find enthalpy of the reaction. If you use moles of the solution, you will find enthalpy of the solution. If you use moles of the salt, you will find enthalpy of the salt.
So how do we know it's asking for enthalpy of the reaction when it just says find change in H in kilojoules per mole?
You don't. It needs to be labeled.
Okay, cool. I was like, am I missing something?
No.
Because I don't know. Okay, got it.
Yeah, it should be labeled.
Okay.
Good question, Cyrus.
And then that last column there, change in H of what's the subscript LV for?
So LV is the it's like a published amount. It's an accepted amount. So it's like someone did this in a professional lab super, super carefully, and then it was peer reviewed and double checked.
It's a comparison from what you got to what is generally accepted.
Yeah, so it's a generally accepted delta H. And so by looking that up, which I can just give that to you next class, because I think I might have to look it up in like the Merck index, which is not online. So I can give that to you next time. But basically it's showing us like how close are we.
Sweet.
Yeah.
Thank you.
Yeah.
Bye-bye. Have a great day.
You too. Anyone else have questions?
How would we find the mole for the reaction? You said that we could use the moles of the base or the moles of the acid, right?
Yeah, because I think, do I have data here? I don't have my data up. Okay, so the sodium hydroxide was what, 3 molar? Yeah. And we had 100 milliliters, so times 0.1 liters. So it's a 0.3 moles of sodium hydroxide. And it's the same for hydrochloric acid, because hydrochloric acid was also 3 molar, 0.1 liters, 0.3 moles. Okay, so how many times can this reaction happen if it's a 1-to-1 relationship? It can happen 0.3 moles of a time, right?
Yeah, that makes sense.
Yeah, so it's helpful here to think of moles. Remember that 1 mole is an actual number, right? It's 6.02 times 10 to the 23rd of anything. So if you have 0.3 moles of donuts, you have an actual number of donuts, right? If a reaction happens 0.3 moles of a time, that's an actual number. 6.02 times 10 to the 23rd times 0.3 is, oh my gosh, that didn't work, is 1.806 times 10 to the 23. So with the amounts that we have of sodium hydroxide and NaOH, this reaction can happen 1.806 times 10 to the 23rd times, which is 0.3 of a mole of times. So you divide by 0.3.
Okay, thank you.
Does that help?
Yeah, that helps.
Okay. Paisley, do you have a question?
No, I was just seeing what she said, but never mind,
Okay.
I got it now.
Okay, sounds good. You're welcome. Have a good afternoon.